for one session of the conference. It's a great pleasure to introduce Professor Naccache, Professor to be talking about product of small primes and Cryptology according to the
Okay, so thank you very much, and thank you for the invitation. It pleases me much to be here with you. So I would like to use the hour that I have to address applications of product of small primes, and this is going to be the theme, which is going to be the cement of this talk. And I'm going to overview applications, quite astonishing applications of products of small primes, and see that in computer science and in math in general, we can do many, many very diverse things with this primitive. We will see how we can use, or how those products of small primes were used in the original proof of Gödel's theorem. We'll see how to construct with them public encryption. We'll see how to construct with them error correcting codes. And we'll see also very astonishing applications. For instance, one application where we will be doing file reconciliation between, so it has nothing to do, actually, usually these are not things that you would attack with number theory. How you do file reconciliation between, let's say, Dropbox server and your PC in a very, very efficient way using products of small primes. So let's start with the first application concerning Gödel's theorem. So as you might know, but maybe people are not from the field. I'm personally not from that field, but it's interesting to see and understand how they were used. In 1930, Gödel proved this very famous theorem, which is called the incompleteness theorem. And I would like to recall how what this theorem means and how this theorem was proved. So it's very interesting to have a first look at this. So very much simplified in a few slides, and you could use those few slides to give a graph of Gödel's incompleteness theorem to your students and so on. It will allow you to concentrate a proof of it in 3 or 4 slides and understand really what the theorem was about. Okay, so what did Gödel do? He started by assigning a positive integer to each propositional calculus symbol. So in a way, this is quite similar to ANSI or ASCII codes. He decided that, let's say, this first logical symbol, the negation, would be associated to 1, and this one to 2, this one to 3, and so on. So assign each symbol, the first 12 useful symbols, encode them as integers that are smaller than 12. And here you see the English meaning of each of these symbols. So this is the first part. So now, once you have done this, we can have variables, and variables they are unlimited, because when you write a theorem in mathematics, you can have P1, P2, P3, and as many P as you want. Same for Q and other letters. So what he decided is that he said, I'm going to just divide, because I have 3 types of entities, of objects that I want to represent. So I'm going to represent one type of objects by encodings that are multiples of 3. One is congruent to 1, and one is congruent to 2 modulo 3. And what are they? You have propositional symbols. So when you see 12, 15, 18, and 21, and so on, you know that this is a propositional symbol. If it is a variable, then you have something which is congruent to 1, and if it is a predicate, then you have something which is congruent to 2. And you have an infinity of those. So now with those, he said we can encode as a sequence of numbers. You give me a theorem, and I can translate this theorem and write it as a sequence of numbers. We say, okay, it would be good, for a reason that will appear later, to assign to each theorem simply one number rather than a succession of numbers. So he said, what should we do to not to have any ambiguity? Because if I would say, let's say I concatenate 2 and 16, you don't know if it is 21 to which I concatenated 6. It is not a real mapping into the numbers. So he wants to have one theorem or one statement, one number. So how do we do that? Well, that's easy. And it connects exactly to the theme of this talk. You take the first primes, so you have 2, 3, and so on, and you raise each of those primes to the power of the integer associated to the symbol. So you can see it here. I did it in different colors, so it would be easy to see. And I calculated on Mathematica. If I write that for all x, p of x is true, okay, then the number that I'm going to associate to this statement, to this expression, is this number. So I have one expression, one number. And actually, this number is called the Gödel number, and the Gödel number is written Gn, abbreviated Gn, of the statement that I translated. So far I have a way to map any statement. You write any sequence of characters, any statement that you want in mathematics, and note that it can be incoherent. You can open two parentheses without closing them, never, but I can still translate them into a number. Good. And now I'm going to show you how this encoding information of information that is introduced in the 1930s can be used to do many nice things. So let's go back to the theorem of Gödel. So now what Gödel observes, he observes something very interesting. He observes that sequences of statements can also receive generalized Gödel numbers. So what is a generalized Gödel number? Now I have a sequence of statements. So let's say you tell me this, and then that, and then this, okay? It might not make sense at all, okay, mathematically, but you give me this sequence of three statements. And I can encode those statements as one number, and how do I do it? I actually encode them as a higher order Gödel number, meaning that first of all, you encode each of these, as I showed you before. And you get numbers that I call A, B, and C. And once you have done that, you plug those numbers into small primes again to get this number. Now, if you want to decode what is the number which is encoded there, what you would have to do, you would have first to take the Gödel number that represents the sequence. Then you take the first, the multiple of 2 that you can find inside. So you extract all multiples of 2. You extract the log in base 2, you find A. And then, once you found A, you factor A over the small primes to see what's inside, and you can write this expression. And then you can do the same thing for the 3, and you get the expression which is this statement, and so on. So now the proof of the incompleteness theorem of Gödel actually depends on the fact that in formal arithmetic some sequences of statements prove other statements. So for instance, when we've been in school and we were asked to prove some theorem, I said, please prove this theorem, you would actually get a good mark when you would align sequences of statements that lead from what you're asked to prove to the target of the proof. Okay? So a correct proof, what is a correct proof? It's a sequence of statements. So if I ask you to prove to me this, and you start from the axioms, or you start from something which is given to you and you mix them and the sequence is correct, you pass through an allowed rule from the previous ones to the next one, and you construct each time where the second might be related or not to the first, but the third might be related or not to the first two, and so on and so on. So you have like this graph, and then at the end you arrive somewhere. This would be a proof. So what is a proof? It's an ordered sequence of statements. So what was the observation of Gödel? The observation of Gödel was that there is a relationship, which is a mathematical relationship, a plain mathematical relationship, which have greater than or equal to, exactly the same, between targets of proofs, which are things to be proved, and numbers that represents the sequence that prove them. Okay? So he said this is exactly a relationship which is similar to greater than or smaller from. So you can just say, we can assign to it a symbol, so rather than saying the greater than or smaller to, it's pure relation between numbers. Okay, it's a pure relation between numbers. You can see it as, for instance, I can have a relationship between two numbers, which is this number contains this other number when written as a binary sequence. Okay, so I have a number which is 100 bits, and I have another number which is 15 bits, and if these 15 bits I can find them anywhere in the binary representation of the big number, then I say it's true. Okay, so it's like greater than or smaller than. So it's a relationship between numbers. So here as well we have a relationship between numbers, which is, we call it RXV, which means that X proves V. Okay, what do I mean by X proves V? If I take X, I break it into a sequence of statements, and if I take V and I break it into a statement, okay, then whatever is encoded in X correctly proves V. It's a proof of V. And then R of X and V are true. So it takes two integers, and it tells you yes or no. Okay. So to ease understanding, I placed it in that order. Gödel's in his proof, he doesn't place it in that order. But why did I do it? Because it's like X proves V. It's like an assignment. Okay. So when you break down what's inside, it proves what's here. Okay. So so what happens? So R, E, and D, where you put inside two numbers. Well, what you mean here is that the sequence of statement which Gödel number is D is the proof of the statement, or a proof. Okay, it's a proof of a statement which Gödel number is E. So this is what this says. So now let's imagine that we are floating in space. Like I saw this movie, what's his name, with Sandra Bullock and this guy who got married recently, the Naccache guy. So assume that we are floating in space. Okay, and we have in space a huge table, and this huge table has integers here and integers there. So it's infinite. Okay, it's positive integer. So I'm here at 0.00, and I see this stretching into deep space, and it's infinite. So now, what I can do is assume that these ones here, this axis, are integers that correspond to proofs. So these are different proofs. And here, on this axis, are integers that correspond to targets of proofs, theorems that I want to prove. And the question I'm asking you is, let's color this space in deep table with different colors. If this sequence of statements proves this statement, then I'm going to color this cell in green. Okay, so I'm going to have a green box somewhere in space. If, on the other hand, I would have gotten 0 if I would have written this when I was in high school, because the proof is wrong, then if this proof does not prove this number, then I color it in red. But then I have another color that I have to foresee, which is, I don't know, gray or black. What happens if I write open parentheses, open parentheses, open parentheses, open parentheses for all? Okay? So this one doesn't prove anything, it's just incorrect. Okay? I mean, it's syntactically, it doesn't mean anything. So this one, let's color them in gray. Okay? So now I'm here at point 0, 0, and I'm looking at floating in space. I'm looking at my table, and what do I see? I see nearly everything is gray. The universe is gray. From time to time, you find some red spots, and there are some green spots, which are miracles, and that as mathematicians we look for during our career. So, okay, that's basically the universe. Now note that you can have one proof here, meaning one column here, where you have several green spots. What is that? It means that during your proof, you proved several results, okay? Like a lemma, and then your theorem, okay? So this would be like green, 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 and green. And also, you might have some lines on which you might have green, 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 which means that because your theorem is correct, you might have several different proofs for it, okay? So you're in Hungary, so you all know about the proofs from the book of the famous Hungarian okay? So the proof from the book is very, very far, probably somewhere there, okay? So, so this is our universe, and we're all happy with it. The only problem is that this is not the universe. And this is what Gödel shows us. He shows us that this simplistic view of what happens in deep space is just totally incorrect. And that we cannot say that we have a gray, red, and blue. There must be something else, some other color. Okay? We cannot just have a gray, red, and blue. So to simplify, what we do is let's first assimilate all the gray to red. I don't need to do it, but let's do it. So now I colored all my space nearly in red, and I have some green spots, meaning that if something doesn't mean anything for me, it's false. Okay, I don't care. So I have everything which is red and some green here. And let me show you that he shows that there is something else. Basically, there is brown. There is also another color which is brown. So what is this color which is brown? The punchline of Gödel is the following. Now, take this statement there that we write here. For all x, x proves v is false. X does not prove v is false. What does it mean? It means that v is actually unprovable. That's all it means. You exhaust the for all x is an exhaustive search machine. It tries all the numbers, one after the other, and it gets rejected at each attempt. Once you plug v inside the R. Okay, so v is unprovable. Okay, so far nothing. There are things that are provable. Whatever is false is not provable. Okay, so so far nothing extraordinary, but this has a Gödel number, and the Gödel number of this statement is here. You can compute it, and we can write it down. But instead of computing it, because it's a big number on Mathematica, I just call it R. I give it some numbers. When you see R here, you don't imagine that R is a variable or something like this. Just imagine digits. I mean, you can really compute it and write it by hand. Okay. So now let me consider the slight variant, which is this one. So the slight variant, which is this one, is the variant where I took this, and instead of putting v there, I'm putting the real hard-coded value R here. Okay, meaning 1, 2, 3, 0, which is this number. I'm hard-coding it here. Okay, so now we consider this statement. Okay, so what does this statement say? How do you, what it says? It says that no proposition that says whatever is in R can be proved. Okay, and what is in R? What is in R is that no proposition of type V can be proved. Okay, but this same proposition is of type V. Okay, so this same proposition is type V. Okay, so it collapses into what? Into the statement that this proposition cannot be proved, which is inconsistent, because if it is provable, then it cannot be proved, and vice versa. So what does it mean? It means that in our infinite table, there are those boxes, those cells, that turn from red to green, from green to red, from red to green, from green to red, and this at a very, very quick pace, and when you mix red and green, it gives you brown. Okay? So You see how this tool was used by Gödel to prove the incompleteness theorem. It's very interesting that all of a sudden someone resorts to this. And it is not a coincidence. It is also because this gives us a unique representation in a given way of information, unique mapping. So now 40 years pass and Diffie-Hellman invent public key cryptography, so you're all familiar with that. And they proposed their new revolutionary manner to produce a unique pair of physical objects. You all know how you do it. You take two padlocks, you close one, you send to him, you close one, you send to him, and then each of them can manufacture the same physical object. And even if the attacker was collecting those padlocks, then he cannot do anything with it. He cannot take two padlocks. And it's exactly the Diffie-Hellman pair of unique objects. So this is based on the discrete logarithm problem, and this is the analogy of how Diffie-Hellman do it. So now we're going to use the Gödel encryption to do public key encryption. So here, what we're going to do, we're going to generate a large prime P. Think about it as a 1024-bit prime. And you select a large secret S. And you publish the S powers of the small primes. So Pi is a small prime, like 2, 3, 5, and so on. So you take a big secret S, let's say, think about it as a 200-bit number, or 500-bit number, P as a 1024-bit number, and you take all the small primes, and each small prime you raise to the power S, and then you get the VIs. So the VI is the power modulo P of a small prime. And now you have a message M that you want to encrypt, and I denote it bits M1 to MK. So you have K bits. And what you do is simply this. You compute this ciphertext. Now this ciphertext looks complicated, but as a matter of fact it is really not, because what happens is that, do we have a battery here? No, even not. Oh, here I see some laser. Oh, good. So this here, once I was astonished by I was doing some presentation in one institute, and they had this laser presenter, and I saw a warning on that, so I glued this. Was said, do not look into the laser with the remaining eye. I don't know if it was. I don't know if it was. You know, in the same vein, I'm a smoker, and I had this advertisement on this, like, smoking kills and all those things. So I edited some which are the same size, which are saying war is bad, all sorts of moral things like this, and I show it to people, and they say, they write this now, good. So many people don't realize. So okay, so the MIs here are just bits. So actually, what happens is that those bits are used to select some VIs and not to select others, because this is a bit, so when it is 0 I don't take, and when it is 1 I take. It's not really raising to a power, it's just that it allows to, in an efficient way, to compute, to represent the product. So this is the encryption, this is the ciphertext, and now I want to decrypt it. So when I want to decrypt it, all I have to do is take this ciphertext, raise it to the power of S, which is here, the big random key S, the secret key S, modulo P, and then what happens is that this has the effect to shrink everything back to my product of primes. Now, if the product of all the primes is smaller than P, which is a parameter that I can set, basically I multiply all the primes, all the K primes that I take, and I take P as being the prime which is bigger, immediately bigger than the product, then this decryption works. And then I can retrieve, by actually factoring this, the different prime numbers that I have here. And this gives me actually the plain text. Okay, so factoring this over the integers, or actually just taking GCDs with the PI, allows me to determine n. So again, this small strange primitive, which is a product of small primes, allows me to do what? To do public key encryption. Okay? And if you're interested in that, you can look at the underlying problem which is related to the discrete logarithm. And here is a CA example. You have these small primes, you have this secret here, this is the public key, you have the public key here, and then you want to encrypt this number, so you would compute this product, you want to repeat, if you do that, and you can see that if I raise it to the secret power s, which is this number, then all of a sudden it shrinks back to a small number, and this small number can be written factored on that base and give me exactly in the exponent vector exactly the number that I had here. And there are other crypto systems that use this idea, notably in the exponent. So there are systems based on higher residues where you work modulo n, but where the phi of n is generated in such a way that it has big prime factors and many small prime factors. As a matter of fact, you generate phi of n first, and then you test for the primality of the factors, and this allows you also to do public encryption. Now let's turn into something which is a little bit a way of crypto. So we have been the way of crypto, and now we go further away from crypto. Now, what I told you at the beginning of this presentation, we are doing a Dropbox, and we want to just back up information on the cloud. So we have Alice and the server, and Alice has a collection of files, F1, Fn, and from time to time she's synchronizing her files with the backup server, which is this one. And the server has a list of files which is only partially conform to the files that Alice has. Basically, there might be files that Alice has and that the server doesn't have. These are new files that has been created. Files that the server has and that Alice doesn't have. These are files that Alice had and that she erased. And then files that are in common between the two. So files trivially fall into these three categories. And what we would want to do is that we would want Alice to efficiently update the server, okay, to back up. So this is something which is very currently happening. So you would say, okay, so we are using tools such as rsync. So let me invoke rsync, which is a very useful tool, and it will synchronize the two parties. But if you're using rsync, rsync is actually transmitting a quantity of information which is proportional to the number of files that you have. Rsync works with hashing. So what rsync does, you can take the code. It is in the public domain, and look at what it does. It takes all your files, it hashes them, and then it begins to exchange information about the hashes, and to determine which file exists by both parties, identify which files do not exist, and then progressively settle the thing. So if you have 1 billion files, well, rsync is going to transmit information which is proportional to 1 billion. If you have 1 trillion, it would be proportional to 1 trillion. Okay. And what we would like to do is we would like to transmit as little data as possible. And ideally, what you would like to do is transmit a quantity which is only proportional to the difference, but independent on the number of files that you have. So the question seems to be a little bit difficult, because how can I know what you have? And basically, is do I know that I have a sister? How do I know that I have a sister? So you don't know me. You don't know what you might know. My family might not know. So so how can I if I bound you to exchange only the size of the difference, how you can settle? And as a matter of fact, this is something that is doable, and it indeed gives you a protocol which is much quicker experimentally than rsync. Okay, but it uses lattice reduction and number theory. So a computer scientist, that would be, what is this? This is very strange, because, I don't know what is this at the end here. Please disappear it, put it in Anyway, I don't need it. I will tell you orally what was written here. So now I take a large prime P, and to fix ideas, think about it as a 1024-bit prime, and I denote by mu of f a function hashing a file into a big prime, a prime which is 160 bits. So we say mu is going to hash the data into a prime. You can first hash and then look for the next prime. This is not very good, but think about it as something that hashes into a prime. For our purpose, it is fine. And now the tool that we're going to apply is the LLL algorithm. So the LLL algorithm will come to it later, but it is going to give me the possibility to do the following thing. You give the LLL P, and you give LL, which is a 1024-bit number, and you give LLL an X, which is a 1024-bit number. And basically what LLL does, LLL rewrites X, it packs the information which is in X into two numbers A and B, where A and B are of half size. So it's a way to basically take all the information that you had here. Here you have an entropy of 1024B, and you take it and you divide it into two packs, one of 512 here and one of 512 there. So it just allows you to share the information. And as a matter of fact, LLL can allow you to share the information in any way you want. You can, if this is 1000 bits, you can do 100, 900, you can have 800, 200, any way you have like a cursor and you can set wherever you want. So here, what we do is that we say let's do 512 and 512. And you can convince yourself by a counting argument that such a writing exists, because if you look at the number of targets that you can generate, if you have A and B that vary and each of them is 512 bit, you see that essentially what you are counting is a space of 2 to the 1024. Okay, so it's just an expression, a different expression of the information which is here informally. So how it is done is a bit technical, so you could ask the session chairman, who is the specialist, to explain to LLL. He is working on implementing it. But we don't need actually to know how LLL works. We're just going to use it. So now I'm going to use this to do this protocol. And the protocol is a two-pass protocol, meaning that it is the most efficient protocol that we can imagine in computer science. Is that if you have two parties, the two parties, each one is saying something to the other, and then you've done the job. You cannot do this with less. Otherwise, it's a monologue. If you want to have LLL information, you can refer here. So this is the protocol. So here is what we're going to do. So the server, the server says, okay, I want to get updated. So what is going to happen? It's going to take all his files and hash them and multiply the hashes modulo P. So these 160-bit numbers, and you reduce it modulo P. And then you send this resulting U to Alice. Alice does the same for her own files, but divides what she gets modulo P by the U that the server sent her. Now she uses LLL to write this X as a modular ratio of A over B. And now what she does is that she takes A and she factors A over the base of the hashes of her file, meaning that she just tried to see if the A that she got has in it the hash of F1 or the hash of F2, etc., etc. Now, whenever she finds that in A there is a hash of one of her files, what does she do? She adds the hash of this file to some set S, which is the set of files to be sent to the server for update, meaning you don't have those. I found one that you don't have. Now, in B, what would happen? That Alice gets in B a pack of information that represents the files that he has and that she doesn't have. If she would have wanted to know what's inside, she would have had to factor this B. But factoring this B might be a tedious operation. And anyway, Alice doesn't need to know what are those factors because she doesn't have those files. All she needs to do is inform him of B. So what she does is she just takes B, puts it along with S, sends this to the other side, and he's doing the same thing and deletes all the files which are in B that actually Alice doesn't have, and hence he adds S to the disk, and they are settled. What did you transmit here? You transmit 1024-bit number and the information that you need to update, and here a half-size number which is 512 bits. You say, okay, all this is nice, but what happens if the difference is big? Here we have 1024 bits number in P. I told you it's 160 numbers in each of those. Okay, so what happens if I have a difference of 200 files? So 200 times 160 bits is much bigger than 1024. So we're going to have here a sort of mashed potatoes, and when he will try to he will not be able to factor this, and when we have to factor that, it's not be integers anymore. It will not fall. Basically, this annihilates the modulo P effect. This is the idea, is that LLL would annihilate the modulo P effect if the difference is small enough. But if the difference is too big, then I've got here sort of mashed potatoes, and I will not be able to know what is in A and B. So what will happen? What should we do? We should resume everything with a bigger P, throw away what we have done. Well, as a matter of fact, we don't need to throw away. We just need to accumulate information. And what is the idea? The idea is that if this happens, if the difference is too big, okay, I keep what I've done, and I say to the other party, now let's do the same thing that we have just done with another prime, which is P prime. Let's say the prime that immediately follows P, for instance. Okay, so the same size. And now I'm going to use Chinese remaindering, and I'm going to work modulo P times P prime, meaning that now I'm working with double size information. Okay? And now, does LLL work or not? If LLL doesn't work, I say I go to the next big prime, and so on. And when will I stop? I will stop when the factorization here will work. So this means that I'm not throwing away what was happening modulo P. I'm just putting aside information. I'm building the difference, and when it works, then it's fine, I settled. Okay? So this is not a product of small primes. So you say, okay, 2 to the 160 is small for you, David. No. So this is the idea of the Chinese remainder. I don't care what I'm doing, I'm having this and that, and all the quantities are of the form A that work either modulo P or modulo PP prime. If you look at the protocol, modulo P, modulo P, modulo P, everything works modulo P. Okay, so I can use Chinese remainder also. So using hashing into big primes is costly. So and another idea consists in saying, what if I hash into small primes? So if you hash into small primes, this is bad. Why? Because you can get collisions, so you can confuse files. So this means that you can mistake the Explorer for some video game or something like this. But if I do this, there is an observation, is that if I do get a collision cannot create a difference ex nihilo. A collision can only make me oblivious to a similarity. Okay? Sorry, oblivious to a difference. It cannot create a difference that didn't exist. Okay, it just means that two files collide, so I didn't see them. I didn't see that there was a difference. Okay, but it didn't create an artificial difference. So what can I do? If instead of hashing into big primes, what I do is that I have a hash function with where each time I hash the information with a counter, saying now I'm in the hashing round with 1. So I'm hashing M concatenated to 1. Then I'm hashing M concatenated to 2. M hash third round M is concatenated to 3 in these laundry cycles. What happens is that at each of those cycles, I'm going to find some differences. I'm going to find some differences using this. I'm going to be able to settle those differences. I'm going to be able to settle those differences, but some files would have collided. And these I would not see. But I don't care, because then what I do is that I change the mu and I begin again. So for a file to resist, the file has to resist to all my laundry cycles. Okay? It's like when you have a dirty shirt and you put it in the machine for 7 times, 10 times, so some spot has to resist to all of them, and once it got caught, it's fine. So you see that even if you implement this with small primes and you repeat, you can very easily manage to settle the difference. However, here the protocol that you're going to have is not a two-pass protocol because of the collision, but still it is extremely quick. Okay, so now let's see something else. How can I use this encoding of products of small primes to do some error correction? So this is something that I never published. I developed it with Jean-Sébastien Coron, was one of my ex-students, but it is interesting as an application. So now let me give you a few reminders on error correcting code. So this is an ideal communication. You send hello and hello arrives. But in a noisy world, in the real world, this is what happened. Thunder strikes, it becomes hell, and this guy says he was insulted. So he takes a missile, he takes a missile, he's dead. Crimea has become Russian. Okay. So the error correction code, to avoid these problems, what we do is we use an encoding algorithm. You put inside hello and you get this funny string. This is what you transmit. Now Thunder strikes on it and modifies it. This guy would put it into a decoding algorithm, and if the error is not big enough, is not too big, then you will get actually the message. And usually what we talk about when you do this is that we have a little bit of technical terminology. We talk about the correction capacity, which is the number of errors that the code can correct, and the ratio between the encoded message and the original message. In our example, it was 7 characters encoding 5 characters, called the expansion rate, and we denote it R. So here is how we're going to use this Gödel encoding for doing error correction. So it's a bit strange because when you want to correct messages against errors, you wouldn't think about using number theory. Because when you multiply two numbers and you switch one bit and you flip one bit, usually number theory doesn't like it. Okay, it's very intolerant to bit variations in numbers. But still, we're going to use it and show you how we can beat some performances of, under some very particular circumstances, of some error correction code, not the turbo codes, don't dream, but of Reed-Solomon codes that were used before turbo codes were invented. So how do we do it? So okay, again we're using the small primes, and we encode the message exactly as we did before, but this time we have no S. We don't do any encryption. And I'm going to send over the noisy channel this couple CM. Now here K, unlike the case of the public key encryption scheme, it can be a billion. Okay, think about it as a DVD. Okay, so all these are the bits of a DVD. So I take bits, I take the primes and I multiply them. So K can be huge. So P, let's say, is 1024 bits if you want to fix your ideas. But K can be extremely large. It can be 1 billion. So what I'm going to do, I'm going to send to you the message M and this appendix, which is 1024 bits. And for the time being, I'm asking you to do to me some credit. I will settle this debt later. I told you number theory doesn't like when you have errors in numbers. So for the time being, you're going to do to me the credit to that no error happened in C, okay, when C was transmitted. I didn't say anything. But maybe it's when I stop to speak. I try to find what the filter response function. Maybe, yeah. So what is going to happen here is that you're going to give me credit that there was no error here. But later I will explain to you what happens when we do have errors in C. But now for the time being, let's say we don't have an error in C. If I don't have an error in C, what am I going to do? The receiver gets C and some M prime. Okay? He computes the same thing. He does LLL exactly as before. And then this corresponds to what? To the flipped and the unflipped bits. except that instead of having messages as I've shown you before, here each prime corresponds to a bit, okay? So it's basically the same idea as what I showed you before, except that we don't hash. Here we have pre-assigned primes. And again, using LLL, what I'm going to do is write it as a ratio of A over B, using this same theorem, and two numbers of size root of P, factor, and then know which are the bits that U and I had, and basically what is the correspondence between M and M prime. So I can, if I find some primes in A, these are bits that were set to 1 in M and were reset during the transmission, and if I find bits in B, then these are bits that were 0 and flipped into 1. So I can understand what those are, what those bits are. Of course, the correction capacity should be tuned, and we'll see that later, so that the code's correction capacity doesn't exceed the information that you can pack into P. Okay, good. You can do a small calculation if you want to have a given correction capacity and you want to know what should be the size of P until which prime K you're going to go. So this is actually the relationship that you have between those parameters. So you have T is the number of errors that you want to correct. Let's say 17. You want to correct 17 errors on a DVD, which is with a K which is 10 to the 7, let's say. So you get 10 to the 7 times log of 10 to the 7, plug a log here, times 2 times 17, divided by log of 2, and it gives you the size of P that you need to have. Okay? So if you impose on me a medium of size K bits, and you want to secure it against T errors, I will be able to compute the P that stems for it. Okay, so now remember that I had a depth for you. I told you there are no errors that hit C, but errors might hit C. So what happens if C gets corrupted, or even worse, I get an error in both C and M? Okay, so what I'm going to do here is something very curious. So I'm going to apply this same scheme again and again and again and again. I'm going to take C, consider it as a message, and apply to it C, and apply to it C, and apply to it C, and apply to it C. So what I'm basically doing is I'm postponing my depth until some final point here. Okay? So now how do I settle that? Okay? Assuming that I had no error here, I can use this one to correct the one before. And assuming that I had no error here, I can use this one to correct this one, and this one, and this one. When do I stop? I stop when I get to a fixed point where doing a further correction step, giving the number of errors T that I want to protect against, doesn't reduce the size anymore, okay, of this. And then once I got there, what do I do? Well, it's very simple. What I do is then I use duplication. I take the last one, okay, that I reduced as much as I could, and this one, I replicate it 2T plus 1 times. Meaning that if I was extremely unlucky, and it was the third bit of each of those copies that was hit by the thunder, then, because the thunder is allowed to hit me only T times, okay, this is my correction capacity, then even if the error comes in synchrony on the third bit of this number, I will be still able to do a majority vote and spot actually the error. Now, if you don't like to do a majority vote, what you can do is say, okay, so now use your scheme as you do, and I'm going to use, let's say, a Reed-Muller code, some other code that has nothing to do with it, some error correction code, on this number C. And what am I going to do? I'm going to take an error correction code that has interesting properties when C is small, knowing that this error correction code has very good features when you want to correct a small number of errors on a very big message. So basically, you're going to use the advantages of both, and this what allows us to get much better results than, let's say, Reed-Muller alone. So here what you see is basically what you get, and you can see that there are some instances where here what we compare is the Reed-Muller. That's the classical Reed-Muller which is done. These are the figures of Riedmüller, and this is a sort of mix where I first encode M as a C. You see like this as a C here, and then I just use the Riedmüller to protect the C for 31 errors. Okay, for 31 errors. And you see that the K that I'm protecting against here is about 6,000 bits. Okay, so you see that actually what we get, the performance that we get, is the global information transmitted when you use this mixed variant is that for the same correction capacity, but here use that. So there is a difference. You manage to improve. Okay. If you send this rather than a plain Riedmüller of the same operation. Now Riedmüller is of course not the most efficient error correction code, but it just shows you that it's not just a toy example. You can try to do some interesting things with it. Okay, so it is just a descriptive, as I said. We have much more efficient error correcting codes today. So it's the conclusion of this talk, because it's just about time. What I showed you is that how this encoding of information by Gödel can give birth to a proof of the incompleteness theorem, public key crypto system, error correction schemes, and many other things that I didn't talk about here. For instance, factorization algorithms, quadratic seed, most notably discrete log algorithms, on which there was a lot of work recently done by Antoine Jou and other people around the world. It's very much in fashion now. Point counting on elliptic curves, and very interestingly, a very beautiful attack on RSA signature, which is due to the Smet and Odlisko, which was published in the 80s, where by doing algebra on the exponent vectors, they managed to forge RSA signatures. So basically, in this attack, if you sign using RSA by just taking your message, hashing it, let's say into 160-bit hash, and then you apply the RSA function, where they show you how, by finding hashes that break into products of small primes, they can translate the relationship between signatures into a linear relationship on the exponent vectors, and eliminate primes by dividing those hashes, so that they can construct one hash as a multiplicative product of other hashes modulo p, and hence they can get a forgery. It's a very beautiful attack, and if you are teaching crypto and you want to have a nice example of cryptanalysis for your students, you can include this in your course. I hope you enjoyed this lecture, which has esteemed the product of small primes, and I would be glad to take questions if you have any. Yes. Why Gödel? Just that this encoding, I think, allowed him to just simply map into one number. You can, of course, imagine encodings that are that would stem from concatenation with some control. You can reserve, let's say, 00, for instance, and saying the sequence 00 is reserved, and then once you started putting your encoding, you can use it to separate. You can have a dedicated separator which would achieve the same result. You're right. I think that this way of separating numbers, but it's just a subjective opinion of mine, is due to the fact that we are used to computer systems where we have units of data that we separate, and by the time when Gödel did this, what he had is pure mathematics in mind, and he wanted to map into a number. So I think that the most natural thing that he had, not having seen a file system in his life, and not having seen a sorting algorithm or something like this, would be I need to map it to a unique number. So he probably had this idea. So to answer your question, there is no fundamental reason to use this specific encoding. He used this in his paper. I think it is, we would use other encodings as you suggest, but I think that these are coined by our experience, and by the time in the 30s, he was just mathematician saying, I need a unique number. How do I do it? Oh, factorization is unique, so let me create something which factors in a unique way. This is my guess. Yeah.
Somebody from the talk is the full branch of the so my question is about because engines are human form as well. But if you don't full branch, but I can find
oh, of course. If p minus 1 is a smooth number, if p minus 1 is a smooth number, then what you can do is you can actually compute the discrete log in the different subgroups, and then once you got this, you can work your way up. This is, I can give you a few references to see how it works. There are a number of discrete log algorithms that allow you to do it. We just have to take a piece of paper and show you how knowledge of the factors of p minus 1, if they are small, can allow you to compute the discrete log. If it is prime, you can and they are smooth, and p minus 1 is smooth. I can show you how you can very easily. It is also used as a trapdoor here. You can look into this higher residue crypto system that I talked about here, where you have a product of small primes with phi of n. So you have phi of n so you have n, which is an RSA modulus, if you wish, and phi of n is engineered in such a way that phi of n has some big factors and some small factors, and those small factors allow you to compute a discrete logarithm very easily, modulo those ones, and this discrete logarithm actually encodes the message that you want to translate to the other person. So just if you come, I show it. Well, it all depends, for the discrete logarithm, it all depends on p minus 1 actually. If p minus 1 is smooth, then yes, indeed. Yeah? Yes, absolutely. You're very right. If we use, for instance, let's say let's take this crypto system here that I showed here. Where it is? Oh, I'm going in the wrong direction. So if you take the crypto system here, and sorry, here, and if I impose, let's say that what I want is not to No, my computer is fine. I just auto setup, complete video. Oh la la. How do you turn it on? I don't know. Have to wait. Okay, I think that I destroyed everything here. Anyway. Oh, here. I think it is blinking in green, so it will come back. Coming back. So, so to answer your question, let's say that I'm doing. I want to convey to you a session key. meaning that I don't want, like my case is that instead of actually sending to you a message encrypted that way, what I'm going to do is send to you an AES key. It doesn't need to have any structure. And using this AES key, I'm going to transmit to you the message of your choice. Okay? So I'm not that much bound by the encoding of the message that I'm sending to you. I can send you a message which is sparse, that has some bits in it. I don't care. As soon as entropy is enough to convey to you a key, you hash it, use it as an AES key, and I use it. So what happens is that in the example that I showed you, you can get a number of trade-offs, which are, for instance, you can say, I take my primes, and I get buckets of primes. Let's say I have a group of 10, a group of 10, a group of 10, a group of 10, a group of 10. So I say, for instance, here I have 8 of them. So I would say I have 2 buckets. This is one bucket, and this is the second bucket. And I choose one prime here, and I choose one prime there. Only one prime here, and only one prime there. So you see that my entropy was reduced. But on the other hand, I can get very interesting trade-offs in the terms of P, because I can bound the product of the small primes by the largest here times the largest there. So so what I can do is I can say, okay, now I have many of those buckets. Okay, I can have buckets of 4, 4, 4, 4, 4, I can have many of them. I take one in each. So you can see that all those will give you, when you plug the sizes of the maximal primes into this equation, different trade-offs. You can also use other things when you do these encodings. You can also use negative primes. Basically, what I can do is that I can take one of the keys and divide by that key, rather than multiply. And hence, using LLL, what I can do is again write it as products of prime, and then it's not only the total quantity of information, but it is where a number is. If it is up, it will give me an information. If it is below, it will give me an information. So indeed, if the messages are sparse, both in this and in error correction, there are many trade-offs that you can play with. For instance, the error correction scheme that I was talking about, you can try to use powers of primes, using the same prime several times, and also this, meaning that you don't encode binary, but you can encode, let's say, a number in base 3 or in base 5 if you wish, and each of those has different trade-offs. But none of those would actually modify in a fundamental way the complexity that we have. It is more or less. Other questions? Yeah.
You have shown that in that calculation
Well, the computation that we're going to do is anyway polynomial. Okay, so it's anyway polynomial. Here I'm using LLL, but you can actually use extended Euclidean, inversion. To basically, when you compute the modular inverse, you start with a number. If I have to compute the modular inverse of x, you start with x and 1, and then by doing linear combinations, x is becoming shorter and the 1 is getting bigger. And the invariant here is that no matter where you stop, basically 1 over this number times this number gives you x. Okay, so you begin by x over 1 equals x, and then you finish by 1 over x gives you x. Okay, so if you stop in the middle, what you find is a and b. Okay, so you are not actually bound to use LLL, but okay, it's clear. So here you can see that all the effort that you do, either if you extend Euclidean or you do this multiplication, the complexity here is GCD's multiplication, so it's polynomial. It means that the effort, there is no exhaustive search, there is no factorization, there is nothing which is sub-exponential here, but not non-polynomial. So everything that you're going to do would remain polynomial. I think it's probably something like cubic. cubic in the size of the difference or something like that. Yeah. No. This is related to. I passed on it quickly because I have no time. So it's related. It's only related to. There is no security proof. No known attack either. So basically, the discrete log is this, and here you have a sort of multi-discrete log with small prime. So it is so you can say it's based on, but it is not reducible to. Okay? It's like Diffie-Hellman, it is based on secure time, but it's not reducible to. I can give it to you like this. I have. I mentioned several algorithms that were published, notably the Desmetod-Lisko, the things, and so on. But if you want, I can give you all this, and I can give you a zip of all the works that I quote of other people, like the Desmetod-Lisko, the point counting, and so on. So you can have a pack of because I have them on my computer, so I can give you all the. Yeah.
The other question is, when you were trying to find some of my tasks, you were applying, you were doing something question.
This error correction?
No, file.
Oh, this.
At some point,
yeah.
How do you know when to stop?
When you manage to factor. What I do is that I want to you're a server analyst, okay? So we do this. I try to factor here. I don't manage to factor. I don't do this step. I don't say anything to you for several reasons. Because if I first of all I didn't discover anything, so I didn't finish, and I wouldn't want to give you information to erase, which would be erroneous. So I just don't say. But I say, listen, I didn't manage to factor. So now send me another U with the next prime. So you send me U1, now you send me U2. I do exactly the same calculation, meaning that now I'm working modulo U2, modulo P prime, but I'm doing the Chinese remaindering of the same operation. So basically what I would find is the same thing here, modulo P prime. Give it to LLL and say to LLL, write it again now. Now the ratio is not 512, 500, or 1024, 1024. Because P times P prime is bigger. Can I factor A? Can I write A as a product in Z as an integer? Yes, then I do this. If not, I tell you no, pass to the next one. And then I lift. Now note that I don't throw anything. I even don't throw the previously done Chinese remainder and calculations, because I keep my information now modulo PP prime, which has been lifted to PP prime. I keep it, I don't need to redo it. I just ask you for a new one, and then I do a new Chinese remainder with PP prime times P second. So I'm really not wasting anything. I'm just piling up information, and all of a sudden it breaks, and then I say, okay, now I know how to answer to you. Ouais, je te disais, il faudrait que tu candidates sur un poste. D'abord, tu fasses un ERC, parce que tu as des très bonnes chances de voir. Et toi, tu le fasses maintenant, parce qu'en fait, après, tu vas devoir faire un senior. Et tu vas ta starting grant et le senior. Et starting grant, ils te les donnent comme ça. Le senior un peu plus dur, mais ils les donnent quand même, tu vois. Donc, il faut que tu le fasses maintenant. Et si tu veux, il y a un truc aussi, c'est que si tu passes maintenant, I'll give you the talk,
Okay.
and the papers I will send to you. You like?
Great. In the beginning, it's a very enlightened way to see girls.
Yeah, just
Sure.